Hi, welcome back. We're going to cover a little bit of what we did just in the last lecture, and we're going to focus on three formulas that come into play. Okay, the mean, that's just the average, what we used to call the arithmetic average. It's the typical average. We take the sum, that's what this sigma sign stands for, sum of the value x, which is the value we're computing with, times the chances that it happens. So x might be, if you're talking about rolling the number of dots that show up when you roll the dice, that x is going to be the number of dots on the dice that show up, 1 through 6, times the probability of happening, which by the way is 1 in 6. Now the variance is very much the same thing. This is x minus mu, which means the difference between the score you had and average. And then we square it, because it's a distance. Then we take that distance and multiply it by the probability. And if we add all those up, we get what's called the variance. Now, you can simplify the computation by simply changing things around so it ends up looking like this. But frankly, it's the same value each way. Now, remember our birth problem? We dealt with this one before. Let's look again. Okay, this times the probability of each event. 0 girls born in 2 births, 1 girl born, 2 girls born. So my x's are 0, 1, and 2. The probability of this one, like we had before, is 0.25. Probability of this one is 0.50. Probability of this one is 0.25. Now, what we're going to do is find the mean and the standard deviation, find the mean and the standard deviation and the variance. So to find the standard deviation, we're going to take x, 0, times the probability, this one times this one. So 0 times 0.25 is 0. Now 1 times 0.50, 0.50. 2 times 0.25, 0.50. Add them all up. Gives me a total of 1. Now, what that basically tells us is, well, our mean is 1. Now, let's do the same thing with standard deviation. It's going to be 0 minus 1, the quantity squared, times the probability, 0.25. 0 minus 1 is negative 1, times 0.25 is 0.25. Then 1 minus 1 is 0, times 0.50 is 0. 2 minus 1, the quantity squared. And 2 minus 1 is 1, 1 squared is 1, times 0.25 is 0.25. We add these together and it tells us the sum of this is going to be my variance. So I have 0.25, 0, and 0.25 adds up to 0.50. So what I now know is my mean is 1, and my variance is 0.50. Now to find the standard deviation, all I gotta do is take the variance, 0.50, and take the square root of it. That's going to be 0.707107, something along that line. Okay, so this gives us a way to compute the mean, the standard deviation, and the variance right off the bat without much trouble. It's just a simple chart to play with. Now, there are easier ways to do it, and I'll have a slide for you in a little bit that'll help you will show you how to do that. Interpretation. In 2 births, the mean number of females born is 1, and the variance is 0.5, and the standard deviation is 0.707. Notice we only use one variable, because one decimal point, because in my initial data there were no decimal points. So we're going to round this off to 1/10, 1 decimal point, or to the 10th place, and that tells us what we've got to know. The rule of thumb for identifying significant answers. If it is the mean, 1, minus 2 times the standard deviation, 0.707, that's the lowest significant value you can have. If we want to do the highest, we take the mean plus 2 times the standard deviation. So the values are in this range down here, the low ones that are typically not normal. And these, the ones that are high, these are also not normal. And this data in here is where we expect to see most of our data, between -2 and +2 standard deviations. So we found two births. What that says is that we had the mean is 1 and the standard deviation is 0.7. Find the rule of thumb, the outcome of 2 females is significantly higher if it's greater than or equal to 2.4 females. Well, we both know that ain't going to happen. And then we can do the same thing going the other direction. If X successes among N tries is significantly high, the number of successes is a probability of is 0.05 or less. That's considered significantly high. So if we draw a picture of it, if it's, we've got a curve right here that draws a picture of it. If it's way over here on the far right-hand side, more than 2 standard deviations away from the mean, it's considered arbitrarily high and the data is suspect. If it's down here in the bottom, where it's less than the mean minus 2 standard deviations, it looks to us like an odd data point. We need to check it out. Otherwise, the data in the middle is normal. Now, the 0.05 is not absolute. Sometimes if you use 0.01, typically that happens when somebody's going to be significantly injured if we're wrong. So if death is involved, we want the other data point. If, under a given assumption, the probability of a significant event is very small and the outcome varies significantly less than or significantly greater than the original data, we conclude that the assumption is probably not correct. In other words, if we do our computation, we find out that the value we were presuming to be valid is down at the less than 5% range or greater than the high 5%, we say something's wrong. Our assumption has got to be incorrect. The expected value is really pretty simple. All we do is we take the mean times the impact of it and use that as a measurement. So for instance, let's just say you've got $5 to bet. You're in Las Vegas and there's a casino. You can bet 5 on the number. You can bet all $5 on the number 7 roulette. Well, here's my event. I can lose or I can win. If I lose $5. If I win, I gain $175. But what's the probability of this happening? Well, there's 38 numbers on the wheel. 37 of them are losers, and 1 of them's a winner. So the probability of losing is 37 out of 38. The probability of winning is 1 out of 38. So now all I do is take this -5 times this. It gives me -$4.86. And I take 175 times this, and it gives me $4.60, which means my expected value is a loss of 26 cents. So I can expect if I play this game over and over and over and over and over, at the end of the night, the average loss on each play is about 26 cents. Now, if you go down the row and there's the craps table and you want to play dice, well, the way you play it is you bet money and you hope you win. Here's the thing. The chances of winning, well, you're going to bet $5. So if you win, you're going to get $5 back. You get 10, $5 plus your original 5, so you profit by 5. The chance of this happening are only 244 out of 491. So I take 5 times this, it gives me an expected value of $2.49. I can also lose my $5. The chance of losing 251 out of 495. So if I take -5 times this value, I get -$2.53, which means on an average play, I'm losing 6 cents. Now, either one of them's good, but if you got to choose, play this one because you're going to lose 6 cents a play. This one you lose 26 cents a play. You're better off down here. This is expected value, and expected value comparison becomes very, very useful. So what we looked at here is simply how to judge what's going on and how it would impact us as individuals. Typically, since we're dealing with money in this case, we're looking at the pocketbook. That's how it works. Okay, I will see you all next time.